Hey, for this lecture, we are going to look at actually working through a problem, a written problem that can be solved with linear programming, and looking at how it should be structured and what are some of the things you have to think about. So this one isn't so much on the technical aspect of solving a linear program, it's more on the practical aspects of it and the things that you like to see when you're solving a problem related to the real world. So first off, you'll see a file called AMS 2940 online for background. At this point, you need this document. Go and download it. And in fact, stop right here and go work it out. Work out the problem on there as best you can. What I'm going to do in the rest of this lecture is give one possible formulation to that problem. There are many different ways to form a linear program from the information given, depending on the assumptions. So the problem is not 100% clear. There's some variability. There's some assumptions that you have to make. The key aspect is specifying what it is you're solving, what your variables are, however much you can, and the assumptions that you are making. If you aren't taking a variable into account for some reason, state that you're not using this variable at this point. If you have to simplify something, state that you're simplifying it a little bit. So this is more of a judgment, a judgment experience in solving a problem and making sure it's well documented and that what you're solving does give a representative answer and dealing with your assumptions later. So again, go and try solve it on your own, and then we can look through how one possible solution that I'm going to present to it. Okay, so now that you've seen the problem, you can see it has to do with irrigating and producing crops in a certain area. So I'm going to start with these variables. And again, very important when you're solving these things, write out exactly what your variables are as best you can. So here's the variables that I'm going to use for this problem. So PI being the sale price of my crop, I. XI is the area. YI being the production rate, in kilograms per hectare. Fixed production cost of the crop is C. The water cost for irrigation is CW. And the irrigation depth for the crop is WI. And those variables kind of try to encompass all of the things that can change or that you can set or in the problem. And you'll see one of our variables, we actually have a value for it. So CW, the water cost, we actually have a full value for that. Sometimes it's nice to give something a variable, because then you can go back later and say, okay, what if this changes? What's the sensitivity to it? So these are the variables that I'm working with in this problem. So when dealing with complex problems, you've usually got too many variables and you have to simplify. But it's important to note how you simplify the problem. Maybe there's a variable you aren't going to take into account, or something is really non-linear. You're going to simplify it a little bit if you can. Maybe you don't know what a value is and you have to make an assumption on some of the values. Unknown values is a big thing that sometimes you just have to make an estimate and then figure out if your estimate is accurate or not. There are perfectly legitimate steps in doing that, but it's important to note those simplifications. Then you solve your simpler problem, go back and readdress your assumptions. You can do it in a couple of ways. You can look at the sensitivity, so try solving the problem again with different values for those variables to show that, well, it really didn't have much of an impact. Or if it does have much of an impact anyways, then quite often you have to go and find some more information about that variable or model that variable. So for this problem, we're going to make the following assumption. I'm going to simplify it a little bit. So for this problem, we're going to ignore the varying yield for crop based on irrigation depth. So we're going to assume that the minimum depth for each crop produces the yield given in the problem. So we can read the values for Wi directly from the table. So we have the values for Wi. That's a little bit of a simplification. At the end, once we have an answer, we can go back and see if there's a way to incorporate this variable, but we're going to simplify it first and come up with an answer for the slightly simpler problem. But it is important that you write down what the simplifying assumptions are. So objective function. Now, this is coming from taking the problem that you're given and writing it in terms of its variables. So we get this objective function. A lot of these values now, we can take it from the table. We have the value for CW. We have the value now. We made the simplifying assumption around the depth of irrigation. So we have values for that now related to that. So we've simplified this a little bit. And once you simplify it and calculate it all out, you end up with that being your objective function. Still a lot of variables in there, but you can see it's a linear function that we can handle. And we've thrown in a different assumption here. Now this is one that's going a little bit beyond what's in the problem. It isn't specifically written down. It's, if you start to think about planting crops, you know that things can vary from year to year. So we're going to put down the assumption that the yield per hectare doesn't vary from year to year. Reality is that that will probably vary a little bit, but we're going to make a simplifying assumption that it's not varying. Notice that's not stated in the problem. It's something that I kind of figured out from thinking about the situation of the problem. What about our constraints? Well, we have a number of constraints, and so we'll go through a few of them here. First one, water supply availability. We have 10 different crops. We have 10 different constraints for water supply availability. You add them all up, we have a total amount of water supply. That's one of our constraints. And again, here's a couple more assumptions. And the more these assumptions that you can make, assumptions are really the key to doing a good job on a problem like this. So assumption, first off, that it's for the year. We aren't breaking it down by month. And secondly, we can assume that the water availability is steady. So it gives the total water pumping capability doesn't account for availability, because it may be that, even though that's the total amount, it could be that there's less water available in the summer than in winter months, in hot months as opposed to other months. Well, that's an assumption that the water is kind of constant, so you don't have variability in it. Land supply. Again, we have a total land supply available. So you sum up over the 10 crops, it can't be any bigger than that. What assumptions are associated with that? Well, we have an assumption that each area of land grows only one crop per year. So we don't have crop rotations within the year. That's actually a pretty big assumption, but it is an assumption. Crop limitation constraints. The problem says that there are some crops where there are minimums, there are some crops where there's maximums, there's some where it has both minimums and maximums. So that's just putting down those constraints. And finally, non-negativity constraints. So that gives us our problem. Now, there are probably lots of other assumptions, different assumptions that are in there. The more that you can put down for assumptions, the better off your formulation of your problem is, the more complete it is. So now, what about removing some assumptions? What if each land can produce multiple harvests per year, so long as their period doesn't overlap? Sorry, I should have said that at the end of this, you've got a linear program. You can go and solve that out now, okay? So now we're going to look at taking care of some of your assumptions. How do you deal with some of your assumptions? Well, one of our assumptions was that we only had one harvest per year. Or we only had one type of harvest per year. What if we can do multiple harvests? So in other words, what if you can start the year with one type of crop and finish it with another harvest of a different type of crop? Well, if you want to do that, now instead of looking at things on a yearly basis, we have to start breaking it down monthly. So you can look at each month individually and ensure that the total land usage by all crops in that month doesn't exceed the maximum available. So if you look at the table, you can see how the growing seasons are broken down. And you look at January to March. Well, January to March, there's only some crops that grow in that time. We have the limitation of 17,750 hectares. So the total amount in that time has to be less than or equal to 17,750 hectares. Same thing for April, May, June, July, and so on, down through the year. So now we've taken that assumption about the crops per year, which was back on this page, where it assumed every acre of land only grows one crop per year. We take out that constraint and we replace it with this set of monthly constraints. You're going to get a very different answer. Before, you're assuming you can only essentially grow one thing per year. Now this is giving you the flexibility to say, well, what about growing multiple things per year? We've taken that assumption, we've figured out how to incorporate it into our problem, and now we solve again with these constraints. So go ahead and solve this one and see what kind of solution you get with the new set of constraints taking care of that assumption. But now what assumption is in this? There are probably more assumptions in here. You may have things like fields have to be fallow after a certain crop is grown. There may be some crops that can't be grown together. There may be other assumptions like that. Start to document those assumptions as much as you can imagine. One of our other assumptions was that we just dealt with the water supply for the whole year. What if the water supply for each month is considered? Well, with the previous change, we put in crops per month. Well, now what if that water supply has to be broken down by month? So every month only has 1/12 of that water supply available. You can take out the constraint for water supply, replace it with a monthly one, that in January, 1/12 of the water supply is available. In February, 1/12 of the water supply is available. Now go back and solve this one again. See what kind of an impact it has. Does this assumption make a big difference or not? Maybe it does, maybe it doesn't. Try it. Put in the new constraints, solve it with those new constraints, take out the 1, put in 12 constraints, and see what you get. What about other assumptions that are associated with this now? Well, there's additional assumptions that water is needed consistently over the period of cultivation, when in reality you probably need more when you first plant, a little bit less later, depending on the crop. But for now, we have the assumption that water is needed continuously. We also still have the assumption that water is available at the same rate, that you don't have months where there's less water available and months where there's more water available. That's another assumption that's still in there. So again, write down your assumptions. And see, by this stage, we're going through all the different assumptions. We're figuring out, can we incorporate these assumptions? Or are they not important? Or have we gone as far as we can? Maybe we don't have any information on water availability. Maybe we have to live with that assumption, but you put it down and then you know that that's there. Somewhere down the road, you get a little more information. You can put it into your problem and solve it again to re-optimize. Right, thanks very much.